while about how we're going to generate the questions we're going to answer. Remember I said scientists answer questions? When we're doing investigations and inquiry, it's about answering questions. So what we're going to do is look at, I'm going to remind you of essential questions and guiding questions. What are essential questions? Well, I'm going to ask you to see what you remember about essential questions. Because you've seen me use these. I want you to give me a thumbs up to represent true or a thumbs down to represent false. So the first question. The essential question should have only one answer. If you believe this is true, let me take a poll. Okay.
All thumbs are not up.
Yeah, I need to see all thumbs.
They should either be up or down, but they should be in
all,
the air.
all hands should be up. Thumbs should be up or down. Okay. So most of you would say, this is what I'm seeing from most of you, that you don't believe that's true. Okay. The essential question might require definitions be established. The simple questions can have a simple yes or no answer. A good essential question might require some research. Brainstorm just a moment as a class about what are some important questions we can ask to meet our challenge. Oh, wait a minute. Did we develop the challenge yet?
No.
No, we didn't develop the challenge. Well, we've decided what we want to do to meet this standard. So, our challenge is going to be, and we can write it on the board. Our challenge is going to be to design, develop, and refine a device. What's the device we're going to define and develop? What are we going to use here? Rube Goldberg. I'm going to put this for our class. A Rube Goldberg machine is also called a device. Okay? That works within given constraints to convert one form of energy to another. Okay? So, and agreed upon our challenge. Now, don't be surprised if other classes have different challenges. We need to ask, what are the important questions? What are the important questions we need to ask as we pursue this challenge? What type of materials and objects do we need? What type of materials and objects do we need? Or want to use? That is a great question. Do you all think that would be an essential question or a guiding question? Guiding question. So, let's go ahead and write that down. Write that down, and we're going to put a G next to that and see if there's a guiding question. We're going to come up with more questions and see if we can sort of, what type of materials and objects would we like to use? You know? What type of materials and what else did you say? Objects would we like to use? Excellent question. Who can give me another question? Another question. There are a lot of questions we're going to have to answer.
How do we create a Rube Goldberg machine with constraints that we have on the machine?
Sounds like you're talking about what kind of constraints do we need to consider? That is a great question, because nobody even mentioned the constraints. Now, when we looked at the other Rube Goldberg machines, what did we notice they were doing in the end?
It was a whole goal or something.
Okay.
The goal of it.
There was a goal of the machine. So what was the purpose of the machine?
To ring a bell or...
Okay, so one machine, the purpose was to ring a bell. Who remember the constraints do our machine have? Well, let's break it out into two questions. You have it, thank you. And what needs to be the goal? Because constraints and goals are not necessarily the same thing. Yes, Talia. Cross.
How's the device going to convert one form of energy to another?
Very
Excellent.
good. Very good.
Excellent. Let's write it down. How is the device going to convert one form of energy into another?
Cross, I like how you were looking at the standard, because that's part of the standard.
I said, how would the device be designed?
How would the device be designed? See that added up there. How would the device be designed? So in order to do the challenge, what we need to find out as a result of conducting the challenge, what do you need to know before you do the challenge that will help conduct the challenge, what needs to be defined or measured, and what research needs to be conducted. But let's look at our big idea and stuff like that. So the big idea idea, when we do our big idea here in Norwood, it's based on the Ohio 7th grade content statement. So we're just finishing up one, and that's leading into this new one we're starting. So a big idea we were just working on was an earth science standard. That's what ES stands for. And it was thermal energy transfers in the ocean and the atmosphere contribute to the formation of currents which influence global climate patterns. That's what we've been looking at. How these currents affect the climate. Why, like in Norway, Trondheim, Norway, it's so warm, it's that Gulf Stream water. Now we're going to take what we learned about that through the buoys and looking at currents, and now we're going to go into the new big idea, which is a life science idea, and it has to do with what we're doing with Mill Creek and looking at the ecosystem. In any particular biome, the number, growth, and survival of organisms and populations depend on biotic and abiotic factors. That's one thing we're looking at. That's what we do with Mill Creek. We want to see how healthy that stream is. So a biotic factor is something that's living. Okay, bio means living or life, B-I-O, biology, biography, all that. Abiotic is something that is not living. So what non-living factors may affect how healthy an ecosystem like a river is? And think about what we're looking at here. What's a non-living factor that may affect how well something lives there? Sophia?
The sewage or trash.
Right, trash that's in there. Remember, we're doing some chemical tests, so if there's any chemicals in the water, that would affect it. And what are we looking at? With our buoys, what are we going to be testing? Temperature. Okay, so temperature is something that's important. That's why we're testing our buoys. We're going to test the temperature of the water upstream and downstream. Okay? So those are our big ideas, especially we're going from this earth science big idea into this life science big idea. So this buoy activity kind of combines both of them. Our essential question is, how can the study of these global drifter buoys help us to test the conditions in our own backyard? We're looking at buoys, how they use them, and now we're going to make our own buoys. So our challenge is to engineer and release a buoy in a local water source, which will be the Mill Creek, to collect temperature data to help determine the health of the stream. Now this is how we used to do it. This is, I think, 2 years ago. We used to put on the boots and the goggles and have just a thermometer. And when you'd go and you'd have to stand there in the stream and hold it for 3 minutes. Then you'd have to walk downstream and hold it in another area for 3 minutes. And then we just kind of guesstimated the air temperature. Well, that's the old way. You guys are making buoys now. We're going to set the buoy in the water. We're going to have a temperature sensor on the buoy, which is what's going to go on the Frisbee, that will test more scientifically. This will go in the water. That'll test the water temperature for us. And then this part will test the air temperature. So it's a way for us to engineer something that will make our life easier. And that's what engineers generally do. So what we're going to do now is we're going to come up with some guiding questions. You, as a group, are going to come up with guiding questions that will help you be able to better meet this challenge. Okay, so what do you need to understand about buoys to help to make one to release in Mill Creek? Before I go over that, I also want to tell you some materials. The materials that you're going to have to build a buoy, because I don't want you to ask as your question, what materials do we have? When you build your buoy, you're going to have 4 1.5-inch PVC elbows. These are called elbows. They're 90 degrees. Okay? And 4 6-inch pieces of 1.5-inch PVC pipe. Okay? You also have, I think, 20 6-inch pieces of thinner pipe. This is 1/2 inch. This is 1.5 inch. Why do you think this is called 1/2 inch and this is called 1.5 inch? Sam?
Because of how it points in the water.
So what is that called?
Diameter.
Diameter. Is that what you're talking about? The diameter. So the diameter of this is 1.5. So when I say 1.5 inch, that's the bigger one. The 1/2 inch is right here. I think it's the inner diameter. You also have 3-way connectors like this. So if you choose, you can make it a box instead of just a square. You're also going to have 20 of these cable ties. There's 14 inches long to connect everything together. And you'll have a Frisbee. Now, how we're going to test it without using the temperature sensor in the classroom, we're going to see who can hold the most golf balls on their buoy without causing it to tip over, okay, keeping it floating. Now, that's the one I made you. You know, that may not be a very good design. You want to think about if mine is a good design or not. But so you'll have a Frisbee. When we're testing it in the classroom, we're going to test it with golf balls as our payload. When we go out to the stream, we're actually going to put the temperature sensor on it. So you want to keep it dry. Here we want to keep the golf balls from rolling off so that when we really test it with our temperature sensor, it won't go in the water and get grounded. Your group are coming up with 5 guiding questions. What do you as a group need to understand or know to help you build a good buoy that will take this temperature data from Mill Creek? What things will make it easier for you before you can successfully build a buoy? Okay, I've never built a buoy. I mean, that's my buoy right there. You can see it's already coming apart, and I'm not sure how many golf balls that Frisbee's going to hold. What do you need to understand about the buoy? What do you need to understand about the materials? What do you need to know about Mill Creek or the environment we're releasing it into? Each group, we have 5 groups, this will work well. Each group is going to come up with 5 good guiding questions that will help lead you to understand how to meet the challenge. And then we're going to come back together and each group's going to give us their best question, and we'll go over this together. Okay? So right now, you and your group need to come up with 5 guiding questions, things that you need to understand to help you meet this challenge of building a buoy. Okay, so go ahead and get started. The group has to write
How
it.
will
Chris,
we
you
make
guys
the
just have these pages, so you can refer to them.
buoyant? Or how are we going to make it buoyant? Able to float? How are we going to make it able to float?
Starting now, go ahead.
So, each group needs to give me their one best question.
Will it be less likely to flip if the golf balls are on the top or bottom?
Excellent. Sam, what was your group's question?
Should we put more weight and support on top or on the bottom?
Okay.
How will we balance our buoy?
Okay, so how will we balance it? How are we going to support, say it again?
The buoy from the flow of water.
How are we going to support the buoy from the flow of water? So the water floats, or say, so it won't fall over, or?
The speed of the water, make sure it won't tip.
Okay, so how are we going to support the buoy with the speed of the water? So, Chris?
The weather on that day, would it support the way it was built?
Okay, so what kind of weather may not, should we be looking at?
Like rain or
Okay, so that's a good question. If it's raining, what kind of considerations do we have to take into account if it's raining? Will that affect our buoys? That's a good idea. Or if the 4 of you guys went. So we're all 4 going?
I don't think this will.
So 2, can we get 1 in? Alright,
So just like this.
Okay, so we need to see that, Chris.
That one right there.
We need to see that, Chris. We need to use our resources.
What is it doing now?
Oh, I think I know what's happening. As it gets warmer, it's going to get colder. But when it gets colder, it's going to get warmer. We got a reading of like 7 to 12.